Good morning, ladies and gentlemen. Welcome to the first lecture on dynamics of ocean structures. This is an online course offered by IIT Madras under the auspices of NPTEL MHRD. I am Professor Srinivasan Chandrasekharan, who will be the instructor for this course. This course will be covered in 4 modules as explained in the beginning of the website. Today we will talk about the first lecture, which discusses on introduction to offshore structures. The moment we talk about dynamics of any structural system, it is mandatory that we must understand the structural geometry, the form, the function, the serviceability requirements, the environmental forces which are coming on the system, which is supposed to be a prerequisite of understanding a dynamic analysis of any structural system. So, in this couple of lectures we will introduce you to different types of offshore structures very clearly, explaining the structural functionalities of these different forms with respective functions of these kinds of structures. I can be reached at the specific email ID. Whatever query you have, you can always email to me or put it in the discussion box in the website of NPTEL IIT Madras. When we say introduction to offshore platforms, one must understand what is a specialty or what are the different complexities an offshore platform have compared to other conventional structures. One can ask a question, why I need to understand various complexities in the structural geometry of an offshore platform. If you do not understand the structural complexities, it will be very difficult for you to appreciate the requirement of dynamic analysis. Secondly, the methodology and the techniques used to do or perform dynamic analysis either numerically or analytically. Offshore structures are actually being challenged to counteract the depletion of oil resources with new set of discoveries. We all know that oil exploration, which started with shallow waters, has started now moving towards deep and ultra deep waters. So, it is very important that the same structural form or the platform which has been used for shallow waters cannot be used without any structural modification for deep and ultra deep waters. On the other hand, offshore structures are now under great challenge of innovative development, because these forms have got to be moved towards greater water depths. Quest on the research and development therefore on deep water structures is the recent advancement, and that becomes the thrust area of research in dynamic analysis of ocean structures in general. When we talk about development of any offshore platform, this depends on various factors. Structural geometry, which should enable me a stable configuration. The platform geometry should be easy to fabricate, install and decommission. Of course, the developed form or the proposed form should have the lower capital investment as far as possible, what we call as low capex. Any investor or any business organization which inclines in production of oil and gas will always look forward for the return on the investment at the earliest possible period. So, your platform geometry should enable an early start of production, and it should yield high return on investment by increased and uninterrupted production. On the other hand, the structural form what you propose should be well tested, well analyzed, understood both experimentally, analytically and numerically before that form is being invested for practical deployment of oil and gas in the real sea site. It is therefore important for us to understand the response of these structural systems, because selection of any structural system for a specific water depth and specific functionality becomes very important as the primary requirement of offshore structures. This is one of the essential features what we call in the offshore domain as front end engineering design. Front end engineering design is a focus on selection of a geometric form, selected form's viability, its stability and its assurance of yielding a return without failure when the platform is intended to put for a specific critical environmental loads. Now, ladies and gentlemen, before we move on further to understand dynamics of ocean structures, let us ask a question: what are the different types of offshore structures which are generally constructed or which would be constructed? Now, you can categorize them into three forms: fixed type, compliant type and floating type. Under fixed type, you have got two kinds of structures called jacket structures or template structures. The second variety of structure is gravity based platforms. Under compliant structures, you have guide towers, articulated towers, tension leg platforms and spar platforms. Under floating systems, you have semi-submersibles, floating production units, floating storage and offloading platforms, floating production, storage and offloading systems. So, one can have different functionalities of platforms. For example, look at the variety here. We have floating production unit, we have floating storage and there is no production, we have floating production, storage and offloading. On the other hand, depending upon the function, the platform style or the form changes. Let us move on to the first variety of structure, which is called fixed structures. In this lecture, I will give a brief introduction to variety of platforms, only addressing the structural forms of this platform and very brief introduction to their functional requirements, because it is important for us to know the size, the shape, the material, the layout before we start doing dynamic analysis of these kinds of platforms. Let us talk about the fixed structures. We know there are two types of platforms under these braces, what we call jacket structures and gravity based structures. Gravity based structures or jacket platforms in general are come under the single category called bottom supported structures. In general, as the term clearly specifies, these structural systems have a very strong bottom foundation which is extended to the seabed, can be through the piles. Now, the fixed type platforms are also called in the literature as template structures. They rest on the piles, they are permanently anchored to the seabed to resist the lateral and the vertical loads. You can very well understand here, the vertical loads come from the top side of the derricks and other mechanical equipments and the self weight of the platform. The lateral loads come from various sources. For example, it can be from the waves, it can be from the tides and current, it can be from the seismic forces or earthquakes, can also be from the aerodynamic aspects, that is from the wind. We will see all these in detail in the successive lectures of different modules, but let us understand now that the structure is permanently anchored to the seabed to resist the lateral and vertical loads. That becomes the key word here. Now, the superstructure of course contains deck to support other operational activities, which we may not discuss in detail in this particular domain of dynamics of offshore structures. However, there are many other literature referred in my references where you can study to go through and find out what are those other operational activities which will focus or which will make you to understand what are the different types of offshore structures. If you look at the jacket platform complex in general, it contains a wellhead, a riser platform, and let us look at the geometry or the structural form of these kinds of platforms. Why they are called template structures is for a simple reason. The bottom supporting system, as you see here, is comprising of inclined or vertical members. They are braced and they are also having surface levels of interconnections between the joints, so that the whole system is integrated to alleviate the lateral loads or the wave loads acting on them. and of course, these are the points where this will be connected to the pile and the piles will be driven through the sea floor depending upon the condition of the soil, etc. And of course, the superstructure has got various complexities, living quarters, crane derricks, flare boom, etc., which will attract aerodynamic forces, that is wind forces on the superstructure. So, ladies and gentlemen, jacket platforms which has a fixity to the seabed attracts forces laterally and vertically. Let us quickly look at a typical distribution of wave and wind loads on a given offshore platform which is fixed to the seabed. The fixed type offshore structures become stiffer because of a simple reason: the whole template structure is being anchored firmly to the seabed. When they are anchored firmly to the seabed through pile foundations, then the movement of this particular structural system under the lateral forces is highly restricted. Therefore, we say any structure which does not move as far as possible is considered to be stiffer. And therefore, ladies and gentlemen, from the principles of simple mechanics, we all know any structural system which is stiffer in nature will always have a tendency to attract more forces. On the other hand, offshore platforms of fixed type has a tendency to attract more forces. These forces either can come from the waves or it can come from the wind. If we talk about the wave force distribution along the water depth, because this is my mean sea level or the free surface level, this is my seabed where the jackets are anchored to the sea floor using piles. So, the wave load distribution is maximum near the free surface and is practically 0 as it goes deeper and deeper. On the other hand, the free surface effects will impose maximum lateral forces on the platform geometry. Similarly, for the wind, as the height of the derrick keeps on increasing beyond a specific height from the mean sea level, the variation of the wind forces vary non-linearly. We will talk about the spectrum used for wind force calculation, the spectrum used for wave force calculation in the subsequent lectures. So, this figure tells you what are the typical distribution of forces coming from the wave and that come from the wind for a fixed offshore platform as you see here. More importantly, as the platform remains stiffer, the platform is considered to be insensitive to lateral loads. The insensitivity to the lateral load essentially comes from the virtue of their rigidity and the bottom fixity. So, it is a very clear statement here: if the platform is not bottom supported, then the platform would not offer insensitivity to the lateral forces, which we will move on to the next type as we keep on going ahead. There are typical operations involved in construction of an offshore platform. For example, the load out part, the towing part, the launching part, the floating part, the appending part, and keeping them in the vertical position, then anchoring to the seabed and then do the deck mating. The deck is the top portion of this. So, these are different stages as you see here in offshore construction. As we all understand, the dynamic analysis becomes important not only during the load out stage, but also till the deck mating is done. At different stages different kinds of forces are attracted by this platform and the platform must be designed or analyzed for these kind of dynamic variations as they are encountered by varieties of forces available or encountered on them. This picture shows you a clear transportation of a jacket platform. You will see that these are the legs which will be anchored to the seabed through the pile foundation, and they are now interconnected with braces and they are also completely battened and laced, so that the stiffened part of the system is enabling the lateral force distribution along the platform. Of course, as we saw in the last slide, this is now the lying down position. Once it is appended, this will become vertical. This picture gives you again a view of how a jacket is launched using a barge. After tilting the barge, this is actually the barge which is towing and launching. Once the launching is completed, it will be appended and the platform becomes the jacket becomes vertical, and these are the spud cans or the portions where connected to the pile foundation at the sea floor. Once the jacket becomes vertical, then the deck which supports the operational features will be inserted on the top, what we call as deck mating. So, the entire deck which is prefabricated will be lifted using highly designed sophisticated cranes, and then these cranes will place them in position, and there are very specific arrangements how these legs of the deck mate will be connected to that of the installed pile or the installed legs of the jacket, so that they do not move horizontally and vertically as well. Now, let us look at some advantages and disadvantages of the structural form. Obviously, any structural form will have some merits and demerits. Looking at the bottom supported structures or template structures, the primary advantages could be it supports large deck loads. It has got a possibility of being constructed in sections and transported, so modular construction is enabled. It is generally suitable for large fields and long term production because it can support large number of wells. Piles are used for foundation, as you saw in the previous slide, that results in a good stability. Therefore, the platform is able to have good stiff arrangement as it can alleviate the lateral loads acting on them. There are some demerits of this platform. The platform will fail instantaneously without sufficient warning, because that is a general behavior of any rigid or brittle system. The platform is generally not suitable for cyclic loading, because any stiff system will have forces concentrated on the joints. If the joints are subjected to cyclic behavior, then these stress concentration will become higher. The installation process of such platforms is time consuming, and therefore it is expensive as well. The cost of construction of these platforms increase exponentially with increase in water depth. It means such kinds of platforms are not suitable for all water depths. Maybe they are suitable up to 350 meter water depth, what we call as shallow. If it moves further deeper and deeper, the same structural form need to be altered to suit the requirements of greater water depths. These platforms attract high initial cost and of course the maintenance cost, because they essentially use steel, and steel is a corrosive material. One of the main problem which is considered as this kind of platforms is that they are not reusable. On the other hand, since they are founded firmly to the sea floor, decommissioning the platform completely is impossible. Therefore, majority of the substructure becomes non-reusable. The members are subjected to corrosion, which can cause material degradation in due course of the service life, and that will also cause decrease in strength distribution of the members. The second variety of platform, which is also bottom supported, is gravity platform. In this kind of platform, concrete is essentially used as the construction material. They are briefly called as GBS. GBS stands for gravity based structures. Gravity platform, as the word suggests, relies on the weight of the structure. The weight of the structure is so large, the structure is highly massive, therefore, it resists the lateral loads purely on its self weight. There are instances and structures where pile foundation may not become essential. Where driving piles become difficult, structural forms of GBS are designed in such a manner that they can resist the lateral loads only based on their self weight. Piles are not essential for these kind of structures. The heavy mass and the spreading of the mass over a large area of the sea floor causes lot of trouble, what we see in the next slide. The higher mass protects this from overturning moments caused by the lateral forces. Therefore, this kind of structures, as said earlier, are more or less insensitive to lateral loads. These kind of platforms are also capable of supporting large topside loads during the tow out. These platforms have couple of merits and demerits. Let us quickly see them. The merits could be the following: it has got additional storage space for hydrocarbons, constructed onshore and they can be transported in modules, towed to the site for installation. Quick installation is possible by a mechanism called flooding. The use of traditional methods and labor for installation is making this platform time of installation as minimum as possible. Of course, there are some demerits of this kind of platform. It is responsible for seabeds covering because of the large foundations. It causes severe environmental impact. These platforms are not suitable for sites with poor soil conditions because this can enable the platform to settle down in the soil because of its poor offering of resistance to the vertical loads. So, these platforms may not be suitable for poor soil conditions because it can cause settlement of foundation. These platforms has got very long construction period. The natural frequency of the platform fall within the range of significant power of the input wave spectrum, and that cause lot of resonating response of these platforms which could damage the platform. That is a typical photograph or a figure or a sketch we call of a gravity based structure. We can see here this platform has got a substructure, it has got a superstructure. The substructure consists of caissons which are nothing but large cellular bases which are hollow inside. These caissons can be used for storing hydrocarbons which are explored from the seabed. Of course, this has got partly the jacket type structure also which are locally braced and connected. Of course, the deck mating consists of the living quarters, the mechanical equipments, the electrical equipments required, the derrick cranes, the flare booms and the other essential components which are used for oil and gas production. The platform is surrounded by unbraced columns because these are all not braced, these are independent in nature. They are very massive and rest on the seabed by the sulphate. A typical famous platform constructed of concrete is con deep. Con stands for concrete, and when it was commissioned it was one of the deep waters, therefore, we call this as concrete deep water structure. The entire structure was floated and moved in a deep harbor before it was commissioned at a specific location. The second type of offshore platforms is what we call as compliant structures. The variety of compliant structures can be the following: guy towers, articulated towers, tension leg platforms and spar platforms. Now, the question comes, why do we go for a compliant type offshore structures when we already have fixed type offshore structures which are form and function tested? Now, there are many negative factors, there are many demerits of fixed type structures which we now saw in previous two slides. Now, compliant structures are essentially convened to overcome these kind of negative factors. The structural form is generally advisable and recommended. It should attract less or fewer forces in comparison to the fixed type structures. The structure should remain flexible to withstand the cyclic forces which was not possible in the case of fixed type offshore structures. Fixed type offshore structures became increasingly expensive and difficult to install in greater water depths, therefore, compliant structures were thought of. Compliant structures resist lateral loads essentially not by their weight, but by their relative movement, that is why they are called compliant. The compliant word stands for flexibility or movement. Structural geometry enables the platform to move in line with the wave forces. The attaching wires to the compliant tower can counteract the majority of lateral loads by their horizontal component and vertical components. The horizontal component of these kind of guide wires or cables will alleviate the horizontal forces, whereas the vertical component will take care of the additional weight and improves stability. One classical type of structure under compliant systems is a guide tower. The sketch shows a typical guide tower which has a superstructure which has got the flare boom, the derrick crane and other living quarters and other provisions required for drilling and production and processing. It is supported by a tower, that is why it is called as a guide tower. Tower is nothing but a lattice type structural system which is a truss based system. Most interesting part of this platform is that the foundation. Now, this platform does not have a rigid foundation as in the case of earlier platforms, it rests on a spud can which has got a connection which enables the platform to have an hinged motion at this connection. Now, to avoid or to improvise the restoration of this platform under lateral forces, the platform is connected by mooring lines which are anchored to the seabed using clump weights. So, the black one what you see here are the clump weights, these are the seabed anchors which holds these mooring lines down to the sea floor. The tower does not have any fixed connection to the sea floor, it rests on a spud can which imposes a hinged connection to the entire tower. Now, imagine a structural system which is very tall and hinged at the bottom. Under lateral action, the tower will always have a behavior of oscillation like a pendulum. So, it is an inverted pendulum which is hinged at the bottom here, the tower will oscillate. The oscillation, for example, if it goes right, because of the wave forces acting from the left, these guide wires will improvise tension and restore the tower back to normalcy. On vice versa condition, when the tower oscillates to the left, these guide wires will improvise tension, brings back the tower to normalcy. Therefore, the restoration of the platform becomes very easy by improvising alternate tension and compression in these kinds of cables. Please understand that these cables are not taut mode, they are flexible cables, therefore, axial compression cannot be improvised on these cables. So, these cables will be only subjected to pure axial tension, but of course, reduction in tensile forces will cause variation which can result in fatigue failure of these kinds of cables. So, the foundation of the tower is supported by a spud can. This is similar to an inverted cone placed under suction. The upper part of the guy wire is a lead cable which acts as a stiff spring. The lower part is a heavy chain which is attached with the clump weights. Under normal operating conditions, the weights will remain on the bottom and the tower deck motion will be nearly insignificant. During severe storm condition, the weights will get lift off from the bottom. This will soften the guy system and permits the tower to oscillate. Guy lines are attached to the tower below the mean water level and they are close to the center of applied environmental forces which will make the center of gravity and the mass center focused on a specific point which improves stability of the platform. Large overturning moments will not be transmitted through the structure to the base because the base is not fixed but hinged, and we all know from the base of mechanics any hinged connection will not transfer moments from the superstructure to that of the foundation. These kind of towers have salient merits and demerits. These towers are of low cost compared to that of the steel jackets. These towers have good stability as guy lines and clump weights improve stability from the restoration point of view. The whole structure possibly can be reused because the structure or the tower rests only on the spud can, and the spud can be disconnected when it is to be required to be disconnected, and the tower can be made afloat once you release the guy wires. Therefore, the whole tower can be possibly put to reuse, whereas this was not possible in the case of fixed type offshore structures. Of course, they have got couple of demerits. They have got very high maintenance costs because of a fundamental reason. The tower is supported by the guy wires, and guy wires of material essentially steel which are corrosive in nature. These towers are applicable only to small fields because as you see the top side does not have enough facility for production and storage, it can do only exploration and marginal production problems. The cost of this tower increases exponentially with increase in water depth because for the entire depth a steel lattice tower need to be constructed. Essentially a difficult mooring system because the mooring spreads around the tower which will distract or it will cause inconvenience to the vehicles or the vessels moving or approaching the tower for transporting the extruded oil. The second type of platform, which is also compliant in nature, which has got merits better than the guy tower, is articulated platforms. The term articulation refers to an universal joint which is again similar to that of a ball joint. This shows a single unique tower which is connected to the buoyancy chamber and the ballast chamber. Ballast chamber at the bottom and buoyancy chamber closer to the mean sea level which is interconnected to the central tower. The central tower what we call is a shaft here, and the entire shaft is connected to the base using an universal joint, which we refer to as an articulated joint. The upright tower, which is hinged at the bottom, is connected to the base using an universal joint. The universal joint, since being hinged in connection, will enable free rotation about the base, and therefore, the modes of compliancy of this tower are both rotational and translational. In the earlier case, the rotational compliancy was restricted, whereas in this case the rotational compliancy is also made available to this tower. So, this tower is comparatively compliant more than that of the guide tower. The permission of large translational motion could make the platform free from position restraint, and the design introduces a single point failure deliberately. Therefore, that is very dangerous in kinds of any structural design, because if at all the structural design of the platform should fail, it is made to fail in a specific point with the universal joint. The tower is ballasted near the universal joint using a ballast chamber. Large buoyancy tanks are provided near the free surface, which can help us to provide large restoring force, which will cause an anti-clockwise moment to restore the platform when it is under operation. More advantages to introduce double articulation, because there are platforms where multiple hinges are introduced along the water depth as well. The provision of more articulation reduces bending moment on the tower. Fatigue is an important criteria in the design, because this kind of platform system design introduces universal joint which are likely to fail under fatigue loads. The platform has got couple of advantages. It is low in cost, large restoring moments due to high center of buoyancy, risers are passed through the tower, therefore, they are protected from the wave action. The demerits are these platforms are suitable only for shallow water, as the tower shows greater oscillation at higher water depths. It cannot operate in bad weather, it is limited to only small fields. Fatigue of the universal joint leads to a single point failure, which can be considered as one of the important demerit of this structural design. The third variety of platform, which is also a compliant type platform, is tension leg platform. The word suggests tension leg means the platform is completely free afloat, which is connected to the seabed not through the tower, not through the shaft, but only through the cables, what we call them as tethers or tendons. So, the whole structure is completely free floating, which is we call as buoyant completely. It has got columns and the buoyant chambers, or columns and the members horizontally located at the bottom. They are interconnected, and the top side has got almost all details as that of a conventional platform, where it has got a derrick, it has got a living quarters, flat boom, cranes for necessary for operation and production. The top deck mate and the different layers will enable all production facilities of the platform. The bottom column members and pontoon members are set afloat, and they are held in position using cables. Now, why this is called a tension leg, or let us ask a question, why tension or how tension is always in place in these legs. When the platform is made to free float or afloat, the platform is brought to the site, the cables are free to float, the cables are anchored to the seabed using the connections as shown here, and once the platform is deballasted, the platform, because of excessive buoyancy, will try to move upwards. The design is the buoyancy is much larger than the weight. The buoyancy force which is offered in the upward direction is much larger compared to that of the weight which is acting in the downward direction. Because of the large buoyancy force, the tendency of the platform will always have to move up. These cables will try to pull the platform down. Therefore, all these tendons will always remain in tension. That is why this platform is called tension leg platform. This platform is a vertically moved compliant system which has got a taut mooring line. The word taut stands for axial tension of a very high order. The platform has got a very interesting design phenomena. The design phenomena is the platform is designed with excess buoyancy. The buoyancy force is very large compared to the weight of the platform, which will make the platform to held down in position by the tension cables. These cables are called tethers or tendons in the literature. The structure is restrained in motion in the vertical plane and remains compliant in the horizontal plane, which permits surge, sway and yaw motions. The structural action results in low vertical force in the rough sea, which is one of the key design factor of these kind of platforms. It has got a substantial pretension which is required to hold the platform down or to prevent the tendons becoming slack. This is achieved by increasing the free flow draft of the platform and ballasting and deballasting alternatively. The typical natural periods of TLP are kept away from the range of wave loads acting on this kind of sea states. So, in surge and sway period it varies anywhere from 80 to 130 seconds. In yaw the periods will vary from 70 to 90 seconds, whereas in heave, pitch and roll, which are considered to be stiff degrees of freedom, the periods vary from 2 to 5 seconds or maybe 2 to 3 seconds respectively, as shown in the slide. The platform has got salient merits and demerits. It is highly mobile and reusable because the platform is a free float setting body which has got to be anchored to the seabed using tendons. The platform is highly stable as the platform has got only minimal vertical motion. The platform is of a low cost and the cost does not increase with the water depth because in this substructure there is no lattice or the tower except that of the cables. The platform has got very high deep water compatibility and it is capable of anchoring in deep waters and got a very low maintenance cost because most of the structural systems stay above water level. The main demerits of this platform are the following: it has got very high initial cost, the investment in terms of commissioning of the platform is very high, it has got a very high subsea cost, fatigue of tension legs is a very important factor in design and analysis, it is difficult to maintain subsea systems, the platform practically has little or no storage. The other variety platform what we see here is the spar platform. Spar platform essentially consists of a deep draft floating caissons, the hollow cylindrical structure which is similar to a large buoy. The caissons can be a cylindrical system, can be even a truss based system as you see here. The top side of this platform has got similar details as that of a tension leg platform. It has got a flare boom, it has got a workover rig, it has got a drilling derrick, it has got a production deck, it has got a cellar deck, as well as the subsea systems are as similar to the top what you see here in a tension leg platform. Essential features of a spar could be the following: it has got a deep draft hull, it produces favorable motion characteristics, the water depth capability ranging up to 3000 meters. So, these platforms are capable to be installed in deep waters. The drilling and production facilities are available in these platforms. It has got direct vertical access to the production risers. It is surface blowout preventer for drilling and workover operations. It has got steel catenary risers which holds down the platform in position. Inherently stable as the center of buoyancy is located much above the center of gravity. Favorable motions compared with other floating systems. Traditional construction, cost insensitive to the water depth, potential oil storage, relocation over a wide range of water depths, conventional drilling and process compositions available in the platform being used. It has got many merits and demerits: low heave and pitch motion compared to other platforms, use of dry trees, simple fabrication, unconditional stability because CG is much higher than the geometric center or the center of buoyancy, derive no stability from mooring system, therefore does not list or capsize even when completely disconnected from the mooring lines. The demerits are: installation is pretty difficult as the hull and the top sides can only be combined offshore after the spar hull is appended. It has got a very little storage capacity and these platforms generally are not meant for drilling because drilling can cause secondary vibrations for which the platforms essentially are not analyzed and designed. So, in this lecture we discussed about two types of varieties of platforms: fixed type and compliant type. We introduce you different types of platforms with the schematic sketches, the functionalities, the structural design, structural form and variety of forces acting on them with the restoration capacity and to some extent the constructability features. Thank you very much.